You know, for the past few years, the story in AI has been all about bigger is better, just massive, massive models. But what if the next big breakthrough isn't big at all? What if it comes from a model that's literally thousands of times smaller? Today, we're going to dig into this tiny AI model that's making some huge waves and challenging the giants. The real question is this for real or is it just hype?
All right, so here's the game plan. We're going to meet this underdog AI model. Then we'll look at the big weakness in today's transformers that it's trying to fix. We'll dive inside the HRM model itself, see how it was tested, and then, we'll get into the controversy and figure out what the real takeaway is here.
Okay, first things first. Let's meet the model that's causing all this buzz. It's called the Hierarchical Reasoning Model, or HRM for short.
And right away, you can see why this is such a big deal. Look at these numbers. HRM has just 27 million parameters. GPT-4, it's estimated to have somewhere around 1.7 trillion. That's not even in the same ballpark. It's a classic David versus Goliath story, playing out right now in AI.
So get this thing comes out of a small lab in Singapore called Sapient Intelligence, and the promises are pretty wild. It's super small and efficient. It was trained on only 10,000 data points. That's nothing in the AI world. It doesn't even need pre-training. And despite all that, it's competing with the big OpenAI models on one of the toughest benchmarks out there.
So to really get why HRM is so interesting, we first need to talk about a pretty big weakness, a blind spot really, in the transformer architecture that powers pretty much every big AI model you've heard of.
And that weakness has to do with something called sequential reasoning. It sounds complicated, but it's really not. It's just the ability to solve a problem step by step, where what you do in step 2 depends entirely on what you did in step 1. And for all their amazing abilities, transformers are, well, they're just not built for that.
A perfect example is solving a Sudoku puzzle, right? You can't just fill in the whole grid in one go. You have to put a number in a box, then you check if it's valid. If it is, great, you move on. But if it's not, if you hit a dead end, you have to go back, erase it, and try a different number. That whole process of trying, failing, and backtracking is exactly what we mean by sequential.
And here's why transformers struggle with that. They're built with a fixed number of layers. Think of it like a fixed number of steps they can take. If a problem, like a really hard Sudoku, needs more steps to solve than the model has layers, well, it just can't do it. It literally runs out of computational road.
So, how do models like GPT-4 get around this? Well, they use a clever trick called chain of thought. It's basically like giving the AI an external scratchpad where it thinks out loud by writing down its steps. It works, but it's kind of clunky and slow. The huge idea behind HRM is to take that scratchpad and build it inside the model. It's not an external hack anymore, it's a built-in native feature.
Okay, so how on earth did they do that? How do you build an internal scratchpad into a model? Let's pop the hood and look at how the HRM architecture is put together.
So they start with a pretty standard small transformer, that 27 million parameter base. Then comes the first magic ingredient, what's called latent recurrence. This is the key. It means the model's output gets fed back into its own input. It's like it's talking to itself, allowing it to think for more steps without needing more physical layers. Then they add a hierarchy, splitting the model into 2 specialized parts. And finally, the whole thing is wrapped in an outer loop, which lets the model try a solution, check its work, and refine it over and over again. It's basically letting it iterate.
And that hierarchy part is just fascinating. It's actually inspired by neuroscience, specifically how different brain waves work together in a mouse's brain. The idea is to have 2 modules working together. You've got a fast, high-frequency L module that's down in the weeds, processing all the details. And then you have a slower, low-frequency H module that's looking at the big picture, putting all those details together.
All right, so we've got this really clever, brain-inspired architecture. It all sounds great on paper, but the real question is, does it actually work? Let's look at the test results that got everybody talking.
So, remember that Sudoku problem? The one that's basically kryptonite for standard transformers? Well, look at this. A regular transformer of the same size just hits a wall at about 60% accuracy. HRM, with its new architecture, it gets a nearly perfect 99.6%. I mean, that's not just better, that's a whole different level.
But this is the result that really made everyone's jaw drop. This is the leaderboard for the super tough ARC AGI benchmark, and you've got the giants up top, GPT-4o, Grok, and then right there in the middle is tiny little HRM. It's literally beating models like Claude 3 Opus from Anthropic, models that are just astronomically larger. That's kind of insane. But as you can probably guess, when a tiny, unknown model posts results like that, people start asking questions. And it didn't take long for the scrutiny and the controversy to start rolling in.
And this really gets to the heart of it. The numbers look amazing, they really do. But was it a fair comparison? Was the playing field actually level?
So the critics pointed to two main things. First, the cheating accusation, so to speak, was about data augmentation. They basically took examples from the test set, made 1,000 slight variations, and fed them into the training data. The second thing was these task embeddings. This is a bit technical, but it basically means the model was given a big hint about what kind of puzzle it was solving before it even began.
And here's the tricky part. Technically, these methods didn't break the written rules of the benchmark. But a lot of people in the community argued that they absolutely violated the spirit of the benchmark. It's supposed to be about pure reasoning on problems you've never seen before, and this felt like they found a shortcut.
And then came the reality check. The people who actually run the ARC benchmark did their own study to reproduce the results. And what they found was, a much more modest picture. When you strip away the clever training tricks, HRM still outperforms a standard transformer of the same size, but the gap is way smaller. We're talking 21% versus 17%. Better for sure, but not the giant leap the original paper suggested.
Okay, so we've seen the hype, we've seen the controversy. So after all of that, what's the real takeaway here? What's the signal in all this noise?
Well, the general consensus that seems to be forming is that we shouldn't throw the baby out with the bathwater. The benchmark scores, they're debatable. But the ideas in the paper, the architectural ideas, are incredibly valuable. This focus on an internal scratchpad, on recurrence, on this brain-inspired hierarchy, that is the real contribution here.
And one researcher put it just perfectly. He said, look, chain of thought is a hack. It's a temporary fix. It's going to get replaced by some form of internal recurrence. And that's why he says the spirit of the paper will live on. Because even if the results were overhyped, the idea is pointing us in the right direction.
And that leaves us with one last big question to chew on. For years, the mantra in AI has been scale is all you need. Just make it bigger, feed it more data. But maybe, just maybe, papers like this are a sign that things are starting to shift. Is it possible the future of AI isn't just about being bigger, but about being smarter, more efficient, and having a more elegant design?